if we look at a finite class of functions, G1 to G capital N, then by using n times or capital N times Höfding's inequality, we can prove that for all functions simultaneously, I mean, for a large set of training samples, for say 99% of the training samples, for all functions simultaneously, the difference will be bounded by this quantity. And as I said, we can then apply this to the empirical loss minimizer because it will be part of these functions here. So we get the following statement if we use also the fundamental inequalities that allowed us to relate this to actually this quantity. So the supremum over G of this quantity, right? That's the supremum over G of this quantity is an upper bound to that. Or at least twice this is an upper bound to that. So we get this statement here. Basically what it tells us is that our empirical risk minimizer in this finite class will perform almost as well as the best function in that class chosen if we knew the probability distribution, plus some extra factor which goes like 1 over square root of small n. And the size of the class will enter as a logarithm here. Okay, so this is really the most typical form of these bounds. And you always, I mean, you will also see the exact same behavior in the online setting. And this is really very typical. You always have this 1 over square root of n kind of dependence on the sample size and log n type dependence on the size of the class of data. And well, you have this, maybe a note on this log 1 over delta. Delta here is the confidence with which this bound holds, right? So if you want to have a bound for which, I mean, if you want to have a guarantee that holds for 99.9 of your training set, then this will increase. So the bound is bigger if you want to have a stronger confidence. So as I said, this does not depend on the distribution on P, right? This is valid for any possible P. It just assumes that the sampling is actually IID, so independence. It just relies on the independence assumption of the training data. So an interpretation is that if you do empirical risk minimization in your class, you will converge the best function in your class. So that's a nice way to actually solve this problem, this learning problem, at least the estimation part of it. Then for the approximation part, you need to have a class that is rich enough, right? And that's where you see that this log n might enter, because we have an algorithm that behaves well when the class is small. But when the class is small, we cannot approximate all possible functions. And in particular, if we take just linear classifiers, well, I mean, there would be infinitely many, but let's say we take a small set of linear classifiers, then we cannot approximate any possible function with that. So we will pay this price of having too small a class, not in the estimation part, but in the approximation part when we compare this L of G sub G to L of G star. So this estimation versus approximation is really a trade-off. The better approximation you have, the larger your class, and then the worse the estimation, the estimation deviations. So again, just to summarize, so these bounds are valid with respect to sampling of this training data. So they are valid for most of the training samples. And you have this 1 over square root of n behavior and this log n over n if you take into, I mean, this is valid for one function, and then if you take a class of size n, supremum behaves like log n over n. So these are the main facts that you should recall from that. And one possible interpretation is that you should consider that the difference between those two statements is that you have some more variability here because the G is no longer fixed, but also fluctuates with, I mean, changes with the data, right? It's like this, this curve that I was showing before. For a given point in the curve, deviations are small, but if you kind of keep changing points along the axis, you increase the variability of this deviation. So you increase by a factor of log n. Okay, so now let's see whether we can improve these bounds. we can actually go further in many ways. One is that Hoeffding's inequality, if you recall, only used the fact, I mean, it applied to any possible random variable, and it only used the fact that the random variable was bounded, which is the case here because the random variable is either 0 or 1, that's the loss. But we can use more information about this random variable. The other thing is that when we apply this union bound, we kind of looked at the worst case, right? We looked at the training set for which any of these Hoeffding's inequality was violated. So this is kind of a worst case scenario. And also when we look at here, we kind of have a bound that is valid for all possible functions in our sets. And maybe our algorithm does not pick just any function in the set. And actually we know that it just picks one in particular, which is the empirical risk minimizer. So if we know where this empirical risk minimizer might be, then we may have a bound that, you know, does not take into account the size of the whole class, but only the size of the subclass where we know our algorithm will pick the function, for example. So let's focus first on this part, refining the union bound. And to understand what's going on, let's have a closer look at how these binomial variables behave. Because this empirical error is a binomial random variable, right? It's a sum of variables that is either, each variable is either 1 or 0, and we take n of them independent and sum them. So this really, well, I don't need to write. This is really what we call distribution. This P and F, the empirical error, follows a binomial distribution of parameter P and n being the number of samples that we have, and P being the expected value, like the probability that the loss will be 0, the loss will be 1, sorry, which is actually PF, or L of G in the other notation. So ln of G is a binomial variable, or Pn of F is a binomial random variable. We can actually write precisely what are the tails for one function at least. So for one function, we have an equality, not just an upper bound for this deviation. We just, this is the probability that if you take these n instances, or this n independent Bernoulli variable, k of them will be equal to 1. Right? You have p to the k. So for the ones that are equal to 1, and for the ones that are equal to 0, you have 1 minus p n to the k, and this is the number of ways in which you can choose k among n. Right? And you have to sum that for all the k's for which there are enough ones to violate this. Okay? You can try to rewrite it down, but this is exactly summing over all the cases for which this is true, looking at all possible number of ones in the sequence of zeros and ones. Okay? And actually, this is not necessarily easy to work with, and you can have various upper bounds on this quantity, one of them being Hoeffding. So again, I'm looking at the case 0, 1, so I don't have this b minus a that I had in the initially. But you have better than Hoeffding, you can have what is called Bernstein's inequality, where actually p enters. Right? The distinctive thing between all of them, including this one, and Hoeffding, is that Hoeffding does not take into account the probability that the loss is 0 or 1. So it does not take into account this p. So this is valid for any possible value of p. And actually, it's this kind of deviation is reached when p is the worst, which is 1/2. That's the worst case. But then when p is different than 1/2, you can have better bounds, including this one, Bernstein, which has this p1 minus p factor. p1 minus p turns out to be the variance of a Bernoulli random variable with probability b. So the variance of this guy will enter in these inequalities, whereas it does not enter here. Bennett is another version, a slightly more refined version of Bernstein, and you have also this exponential, which is yet another version, and they are in kind of decreasing order of sharpness. So this one is the best because that's an equality. This one is slightly worse, slightly worse, slightly worse, even worse. So Hoeffding is actually the worst. Let's have a closer look at this kind of thing. So if we look at this, for example, Bernstein, we see that there is t here and t here. T is the size of the deviation, right? And we said before, we have a Gaussian kind of behavior for Hoeffding, right? We have e to the minus t squared kind of thing. Here we see that when t is small, we indeed have a Gaussian behavior. When t is large, then these terms kicks in, and then we have e to the minus t instead of e to the minus t squared, which is much more fat-tailed, right? Much more, I mean, it decreases to 0 much more slowly than e to the minus t squared. So we have a Gaussian behavior for small deviations, small t's, and this Gaussian deviation has corresponding variance p1 minus p. And for large deviation, we have actually what is called this Poisson behavior, where we have this e to the minus t independent on the variance. Now p does not enter here anymore. So the tails are heavier than Gaussian. So of course we can upper bound both cases with a Gaussian with larger variance, right? If we just increase the size of the curve, we can enclose both cases, but that's a bit overkill. And this is how it looks. Well, it's not easy to see, but we'll see in the next graph. So these are the actual values. So these are computed with this sum formula, right? And then here are all these upper bounds. The binomial is, binomial, it's this one, that's the exact value. Then we have Bernstein in green. Well, they are more or less all equivalent. And this is for the worst case, p equal 0.5. So for the worst case, p equals a half, you know, most of them are the same. So Hoeffding is okay, let's say. Now, if you look at the case, even fainter, sorry. So if we look at another case like p equals 0.1, then it's not easy to see, but so this is still the exact values in blue. And then, what is this? This one should be Hoeffding, which is the sub-Gaussian here. So Hoeffding is the worst, but then the other one tend to, because they take into account the variance, tend to be closer to the actual values. And that's for the kind of small values of the deviation. And if we look at the large values, so if we zoom in into this area here, then we see that a Gaussian tail. So this is here is the best Gaussian tail that we would obtain if we just say, well, let's assume that it's a Gaussian with variance p1 minus p, which is not true because see, our actual values go above this best Gaussian tail, which decrease very fast. So we have a kind of this heavier tail behavior, which is captured by the other Bernstein or Bennett inequalities. Okay, so how do we use this fact? How do we use the fact that when p, small p, this variance of the function is small, we can do a better job, especially for small deviation? Well, we first have to look at the variance of the function in our class. So we have to look at this p1 minus p thing, where small p here is, as I said before, is the actual loss of the function. And an easy thing to do is to upper bound this by just the loss itself. So if we do the same trick as before, we first apply one single inequality to one single function and then do the union bound. Then for one function, for one fixed function, we have this kind of deviation by just inverting Bernstein's inequality. So we have more or less the same as before, this log 1 over delta over n under the square root, but now times the variance. So that's where the variance enters in this part. And the variance as we said, is upper bounded by PF, so that's what we plug here. And here is the other term that comes from this Poisson kind of behavior. And it happens to be of order 1 over square root of n if you do the inversion. So this corresponds to the e minus t squared, and this corresponds to the e minus t. Okay? So basically, we see that if this happens to be small, then we gain here. I mean, this is always smaller than that because 1 over n always, I mean, at least for large values of n, will be a lot smaller than 1 over square root of n. Yes? I'm bounding it with the quantity I'm trying to estimate. Oh, yes, sure. Yes, the question is, I'm bounding something with the quantity I'm trying to bound, right? Yeah, my goal is to provide a bound on PF, and indeed, I have PF here, which seems kind of useless. But if you actually put all the PFs in one side, then you can get something interesting. And we'll do that in a moment. So, I mean, the point is that this part which corresponds to the Gaussian tail, it's dominating, but when PF gets small, then this will be smaller, and we get a better bound. But okay, let's see how to use that. Let's just assume that we have made this extra step of using the union bound, which is just adding this log n term, right? I mean, I don't rewrite all the details, but we have a deviation. We write this deviation for each function in a set of capital N functions, and we apply the union bound, and we know that this just gives us an extra log capital N factor, which I've written here. Okay, so I have L of G less than LF of G. This term where I have now the log N factor here, the loss here, and this 1 over N term. So now what I will do is try to put all this L of G in the left-hand side to see what it gives me. And I mean, we can use this trick here. We basically have an inequality of the form A less than B plus something times square root of A, right? And I mean, you can easily prove that this implies that you can rewrite things putting A only here and then B and C here as follows. So if I apply this to the previous bound, what I get is the following. I have L now only on this side. Remember that this is true for all G in a finite class, right? Because I did apply the union bound. And now what I have is, okay, so the empirical error. Now under the square root, I no longer have the true error, but the empirical error because of this kind of flipping trick. And basically the same quantities, this 1 over square root of n, this 1 over n, and I have gotten rid of the loss on the right-hand side. Okay, so again, now the bound is small whenever the empirical error is small. So that's what it tells me. Because before I had just 1 here, and I did not have this factor, which in any case does not really play a big role here, but I did not have this, which means that whenever ln is smaller than 1, then I gain something with this inequality. Okay, let's see what is the best such case. The best such case is when we take an empirical minimizer and it happens that the target function, so this G star, is belongs to the class G. So let me explain this better. Before we were looking at the case where we had the class G, and maybe this did not contain. Let's try this way. This did not contain G star, which was somewhere else, and we were looking at functions here, taking the empirical minimizer Gn, and comparing this Gn to the best function. Let's say here, G sub G. So we are looking at this difference, and we said, well, we can't say much about this difference because that's the approximation error that depends on the probability distribution. Let's consider a simple case where we know that G star is somewhere in this class. So in this case, G star is just the same as G sub G the best in the class, right? And we just have to look at this difference here. So we have no approximation error. We know that the true function is in our class. Let's assume that. And let's assume further that the loss of the function happens to be 0. So there is no noise. At every given x, we know whether we should predict 1 or 0. There is no randomness. So in this case, when we take the empirical risk minimizer, we know, because we know that there is a function that predicts perfectly, including on the training data, we know that somewhere in this class, we know that the G star does satisfy this, but let's say somewhere in this class, there is a function which has a 0 empirical error, right? Because at least this one does. So when we minimize the empirical error, we know that there exists a function such that the empirical error is 0. So if we minimize it, we might find it. It may not be exactly G star because there may be many functions that have empirical error 0, and they may be different for different data sets, but at least there is one, so we know that we will find it. So in this special case, which is called the zero noise or perfect classification case, then if we apply the previous bound, because ln of gn is 0, then we have this log n over n behavior and no longer the square root behavior. So the convergence happens to be much faster now. So the estimation error goes to 0 with speed 1 over n instead of 1 over square root of n. Okay, and that's because we used this variance trait. We used the fact that the deviations are controlled by the variance. Okay, so that's one way to improve the bounds. Of course, it only really helps in this specific situation. If ln of gn does not happen to be 0, then we still have this 1 over square root n behavior. Yes. Yes. Let me show you again. If I plug 0 here and here, then this cancel, and just I'm left with just this term. Right? Okay, let's again go to the union bound, and let's introduce a second way to apply this union bound using weights. And the second approach will be to combine the union bound and the variance. So, weights. So remember that the union bound, to get the union bound, what we did was to write some kind of Hövding's inequality for each function. Well, forget about this f. Before we were just writing, okay, pf minus pnf larger than this, less than some delta. And then we were saying, okay, let's sum these things over capital N different functions. So then we get capital N times delta, and when we inverse, we get this log n factor. Now what we do is that we can say, well, we will write each of these Hövding's inequality, but we allow ourselves to choose a different delta for each function. And we'll see why. Let's say now our delta depends on the function. So we write different Hövding's inequality for different functions. I mean, we're perfectly allowed to do this because these statements are true for any delta, right? So, and we sum them up, right? And now we will choose this delta of f, this small delta here, as some fixed delta times some p of f, where now we choose this p as to sum to 1, right? So basically, we give some kind of weight to each function, and these weights sum to 1, and these weights are used to compute the confidence that we put in each Hövding's inequality. Okay? Now we write the inverted union bound, and what we get is that with large probability, where delta is now the fixed value, for all f in our class, deviations are bounded by something which involves, so it's no longer a log capital N, it's log 1 over this pf plus log 1 over delta, which is common to all the functions. So now this quantity actually depends on the f that we are looking at through these weights. Of course, if we put uniform weight, 1 over capital N, we recover the log n that we had before. But we can do something different. We can give more weight to some function and less weight to some other function, and then get better bounds for these functions for which we have given more weight, and worse bounds for the functions to which we have given less weight. The interesting thing is that now this enables us to apply the union bound to non-finite sets, or at least to countably infinite sets. If we have a countably infinite set, instead of writing n times n being infinite, the union bound, we write it with a decaying weight, right? So we just assign to all our function, our countably many functions, a weight such that the sum of all these weights is equal to 1. I mean, this is possible because we can define probability distribution on countable sets. And then we apply this trick, and we will have a bound that is finite, right? We no longer have this log n that blows to infinity, but now what may blow to infinity is this PF, right? Because if you look at more and more functions, the weight to all these functions becomes smaller and smaller, so the log 1 over this weight becomes larger and larger. So which means that for most functions, the bound will be okay, but if we look at the functions in the tail, let's say the bound will become looser and looser. But still, we have a bound, right? And it applies to countably infinite sets. Another remark is that in this PF, if we know something about the algorithm, if we know that the algorithm is more likely to choose such functions over some other functions, then we can as well just put that in the PF and choose our PF correspondingly, and then get a bound that would be better because we would assign more weights to the functions that are likely to be picked, and decrease this factor. But importantly, this P, these weights, should be picked before seeing the data again, right? This in the union bound calculation, this delta of f does not depend on the data, right? It's not inside the probability. It's a deterministic quantity. So we cannot change the weight because otherwise it would be too easy, right? We would say, oh, we know that the function that the algorithm has picked is this one after seeing the data. So let's put all the weight on that function. And then we get rid of this quantity, right? P equals 1, log 1 over P is 0. And then we have the perfect Hovding bound kind of thing. But that's cheating, right? Because we can't really change the weight as once we have seen the data. Okay? So that's one possible way. And okay, these are, again, remarks. Now, another way to use the variance, as we see before, as we have seen before, when the functions have small variance, we can improve the bound. So let's use this trick in a slightly different way. Let's look at functions that actually make similar predictions. In our class, right, this G1 to G capital N, there might be functions that actually always predict the same way or in a similar way, right? If you look at two different linear classifiers, you take this one and this one slightly tilted, and maybe they are more or less making the same predictions, so they are making more or less the same mistakes up to some small difference. So why can't we exploit this fact, right? In particular, this would, if we take two such functions that are close enough, then the probability that they differ would be small, and we can do this by refining the union bound. Let me tell you why or how. When we look at the deviation for a given function, we can introduce some other, let's say, f0 function, and compare the deviations of this one to the deviation of this one. And the difference between those two deviations would actually be something that I write in this way. It's slight abuse of notation, but it means I'm looking at the deviations not of one function, but of the difference between those two functions, right? So this essentially means pf minus pf0 minus pnf plus pnf0. So it's a way to compact the notation, right? I apply this operator to this difference in a way. And this term, if the functions here are similar, right, it means that their variance, as I said before, is bounded by their expectation. So if they are similar, the expectation of this difference will be small, so we'll get a small term here. so if I apply this directly, I get that now, so the deviation for my initial function is the same as deviation for one fixed function f0. That's where I get the normal standard Hovding form, right? Well, I have some extra term, but this is the main term. And then for this part here, because this part has a variance which is bounded by alpha, I mean, assuming that we have this closeness property here, this extra term will give me something which is where alpha, the variance, kicks in, right? And I can apply, I mean, this log n comes from the fact that I apply this to all possible functions f in my class, assuming that all these functions are at distance alpha from f0. Okay, maybe it's a bit confused here. Question? Yeah. Okay, maybe I should have the picture before. So what I'm saying is that let's consider the following case. We take a function f0, and we consider that our class, let's say capital F or G, I mean, F and G are the same things. Let's assume that all functions in my class are at distance at most alpha, distance being measured as the probability that f minus alpha, f different from f0 less than alpha, right? So this is the distance between the functions, and we assume that, I mean, this is some notion of distance between the function, which depends on the probability distribution, of course, but we assume that they happen to all be close, so they happen to all have similar errors, okay? And in this class, there are capital N functions. And what I want to do is to exploit the fact that they are all close to this f0 to get better bounds. So I write the deviations by decomposing the deviations of the f function into decomposing into deviations of the f0 plus some difference term. And what I'm saying is that this difference term, if I apply Hovding's inequality to it, because, sorry, not Hovding, but something like Bernstein's inequality where the variance is taken into account, because of this, the variance of this quantity actually, I mean, it's not completely straightforward, but you can work out the fact that the variance of a function or of a random variable, let's say, let's call it t, that is equal to f of x, y minus f0 of x, y. So the variance of t is actually upper bounded by alpha if we have this, okay? Because these functions are value 0 and 1. So because the variance is small, when I apply Bernstein to this term, I get this alpha factor here. And since I apply this to every function f, I get the log capital N from the union bound. And this term just comes from applying once Hovding to this thing. I just have to apply it once. I don't have to apply it for every function in my class because it's only for a fixed function, f0. Okay, so for these kind of classes, for which all functions are within a small range of a given fixed function, I can get an improvement over the union bound. Instead of having the log n factor directly, I have here something which is no log n, and here we have a log n, but times something which is times alpha, which may be small. So when alpha is small, this is better overall than just log n. And the important point here is that the size of the class, which before was just measured as the number of functions, now depends both on the number of functions that I have in my class and on the geometry of the class. Geometry implied by this notion of distance. And in particular, if with respect to that distance the class is small, I get a better bound. And I can go further. I can exploit even further the structure of the class, the metric structure with respect to that metric. So let's just apply this again. And again, maybe a drawing is better. Let's consider now a big class instead of a small class. But within that big class, let's consider some functions that are such that every other function in the class is within alpha of them. This such set is called a cover of my class. So I'm considering now no longer just f0, but let's say f0, f1, f2, and so on. And I know that every other function in my class is somewhere in one of these balls. So it happens to be close to one of these f functions. And what I do is I repeat the construction. Within each set, I apply my inequality, and then I do that for all sets simultaneously, so I make the union over all the balls. Okay, so that's what I said. This is called an alpha cover, so it's a cover at radius alpha. And the number of such functions that are needed to cover my class up to radius alpha is called the covering number, n of alpha. Typically, it's written n alpha f, which means the covering number at radius alpha for the class f. And if I apply this trick to all these functions, then this log n factor that I would have obtained, where n is the size of the class, is replaced by alpha times log. Within each ball, I have to make a union over all functions, and I have to make the union over all balls, which is n of. Maybe the notation is a bit confusing here, but let's write it better. Or maybe I put this. Okay, so remember that, let's say our big class f has size, well, let's not call it n, but let's call it m. Okay, so m is the size of the whole class. So if we apply directly the union bound, we get a factor of log m. Now, for each ball, we have a certain number of functions in that ball, and we have n alpha f such balls. Okay, so we do have this log of this number of balls that enters, but for each ball, we have this extra alpha times something, and this something is the log of the size of the ball. Because we don't know how many functions are contained in each ball, we just upper bound this by the total number of functions. So instead of saying log of the size of the ball I, let's say we just upper bound these by m, because we know that there are not more than m functions. Okay, so what we obtain is that we have replaced this log m, which was the initial factor, not taking into account the structure, but by something which a small factor times this log n plus an extra term. And hopefully this is better, especially if the covering number is small and alpha is small, then we get a better bound. Okay, again exploiting this distance structure. And well, let's keep drawing. We can actually do better. We can keep doing this and keep applying this trick, because instead of just making one cover, why not making more than one cover? Why not first covering with small balls and then covering with bigger balls, right? And if we cover with bigger balls, then we have to take into account, and in addition to the previous thing, this distance. And we can do that all the way to one fixed function. So basically, we have our class. We start with some f0, which is, say, the center of the class to some extent. And then to reach any function f in that class, we will construct a chain going from cover to cover. So each point here corresponds to the center of a ball in a cover of decreasing radius. Right? So this might be the center of a ball of this size. This might be the center of a ball of this size. this center of the world, this size, and so on. And then we will reach f, which may be an arbitrary function in our class, when the radius becomes smaller and smaller. And what we will have to do is we will have to sum the size of these steps multiplied by the number of points in our cover all the time, repeatedly. And you can prove that if you do that, you obtain what is called the chaining bound, which has this form. So now our log size of the class is replaced by the integral of square root log covering number. Yes? Chaining. Chain, because there is a chain of points. Actually, you can even go further, but the idea is, I'm just mentioning the idea that I won't show you the bounds, but you can actually do this in a way adaptively, because there are some regions where there might be more functions. Like even though your class has this geometry, there might be regions where there are more functions, and in these regions you may want to refine more your covers, but in the other regions which are less dense, when there are less functions, you might want to just have big balls, because it doesn't matter. I mean, like let's say you have just 3 functions here, you don't want to bother and create all small balls here. You just restrict yourself to a larger size of ball. And if you do that, you get even a refinement. But the important point is that we use now the structure to its maximum, right? We're not just counting functions, we are looking at how they are related to each other. Yeah. Okay, so let me just summarize because we are already at time. So here is the summary. Log n, size of the function, is kind of the most simple estimate of the complexity, but a bit too crude. Using the geometry, we can do much better. And using these refined deviations, we can even go further, like going from square root of n to n, when in the good cases. And that's it. Yeah, let me finish here. Thank you very much. Some questions? Yes? That's a very good question, because I said that the covering numbers depend on this probability distribution, right? Because the metric was this p of the difference. It's no longer here, but it was the probability that 2 functions differ. So it depends on this unknown probability distribution. So we can't really compute these numbers, but for many classes of functions, we can get estimates, upper bounds on these covering numbers that do not depend on the distribution. Like for many classes, like linear classifiers, we can get things that depend on the dimension, for example. I mean, you can find in books, you would find many such computations. So it's possible, not directly, but upper bounding them, yes.